So in this video I have some additional questions on the analysis of second order transfer functions. So here we have three second order transfer functions subject to unit step input. So A, B and C. So in these questions I want you to determine the following properties of the system response. So the rise time, peak time and period time, the peak overshoot amplitude, the settling time of a given percentage, in these particular questions 5%, the number of oscillations that it takes to reach the settling time, and then based on this information that you've determined in part A, I want you to sketch and label the graphical output. Okay, a little hint for these initial questions, you're going to have to determine the natural frequency, the damping ratio and the damped frequency. So if you recall question A, the transfer function being given by 4 over s squared plus 3.2s plus 4. Then this is equal here to the standard form for a second order transfer function, k is your system gain, omega n is your natural frequency squared, over s squared plus 2, zeta for your damping ratio, omega n for your natural frequency, s, plus omega n squared. So the first thing we need to do for this question is, if we're going to work out the rise time, peak time and period time, etc., is we need to work out the natural frequency and also the damping ratio of the system, and then work out the damped frequency. So to do that, so if you see here, omega n squared is equal to 4. Therefore, omega n is equal to the square root of 4, which is equal to obviously 2. So 2 radians a second. So we've got the natural frequency. Then if you look at this equation here, 3.2 here is equal to 2 multiplied by zeta multiplied by omega n. We know what omega n is because for the natural frequency we've just worked it out. So we know that. So therefore we can rearrange to make zeta the subject. So effectively zeta the subject here, so 3.2 in this, so 3.2 divided by 2 multiplied 2, which is 0.8. So we've got the natural frequency, and we've also got the damping ratio. What we want now is the damped frequency. So damped frequency is equal to the natural frequency multiplied by the square root of 1 take away zeta squared, which obviously we've just worked out the natural frequency is 2. 1 take away 0.8 squared, therefore 1.2 radians a second. If you put that into your calculator, that's what you'll get. So we've now got the properties that we need to be able to undertake the following calculations. So the first one is rise time, TR. So the rise time is given by this equation. Rise time is equal to 1 over the damped frequency. Don't know why I put equal there. Pi take away tan inverse square root of 1 take away zeta squared over zeta. So if we substitute in the values, natural frequency damped is 1.2, or the frequency damped is 1.2, and then for the damping ratio it was 0.8 over 0.8. And then if you put that into your calculator, just remember, make sure your calculator is in radians, you should end up with 2.08 seconds. Okay, that's your rise time. And at the end we will sketch these onto a graph, so they're visual. Now we're going to look at peak time, TP, and period time, T. So the period time is equal to 2 pi over the damped frequency, which is obviously the damped frequency is 1.2, so we know that this is 5.2 seconds if you put that into your calculator. And then we TP in terms of the peak time. Okay, so this is the peak time whereby you're at your highest in terms of the amplitude of the overshoot on the response, is half of effectively 2 pi over the damped frequency, which is effectively just half at t, which is in this case 2.6 seconds. Right, so we've worked out what t period time and peak time is. Next property we're going to work out is the peak overshoot amplitude, denoted A subscript P. The formula for this is given as follows. So AP is equal to 1 minus E zeta n, well, natural frequency, TP, so the peak time, and then in brackets, zeta multiplied by the natural frequency over the damped frequency, sine damped frequency multiplied by TP to the peak time, plus cos damped frequency multiplied by TP. So that's the formula that we will use. And it's pretty much just substituting the values that we just determined. So as you can see, 0.8 multiplied by 2 multiplied by 2.6, 0.8, 2 multiplied by 2 over 1.2, sine, then the damped frequency is 1.2, TP 2.6, plus cos 1.2 multiplied by 2.6. Then if you were to put this into your calculator, it's probably advisable you do this part here and then this part. It's up to you though. You will get this value. Okay, so that's your peak overshoot amplitude of 1.015. So you can imagine the system's only got a little bit of overshoot. So the next property we're going to work out, determine, is the settling time. So the settling time which is denoted TS, and we're going to do this for 5% settling time. So TS 5% is equal to natural log of 0.05. And to remember, if it was, say, for example, 10%, it'd just be 0.1, 2% it'd be 0.02 over zeta, and then the natural frequency, which in this case, again, we're just using recycling the same properties. So 0.8 multiplied by 2, which if you work that out, it's effectively 1.9 seconds. The final thing we're going to work out, determine, is effectively the number of oscillations to reach TS. So where TS is 5%. And the formula for that is effectively just N is equal to TS over T, which is obviously 1.9 because we just determined it, over T, which the time for one period, which is 5.2. So the number of oscillations, you imagine the system oscillating, the number of oscillations to reach within the settling time, and obviously one period is 5.2, so it makes sense to that, and the value is 0.36. So then part B, what it does is it asks us to sketch the system response. So let's just, first of all, get a nice big, so put time along here, seconds, we'll put amplitude up here. And at the start of the question it said that a unit step input had been applied to the system. So that obviously has a value of 1 in the time domain. So this here obviously in the time domain is u of t. Oh, sorry, I can just about fit that in. In terms of the system response, so if you remember the peak overshoot amplitude, so let's write these values down. So AP was equal to 1.015. Let's just draw system response. It's going to have very little overshoot. So it's going to have very little overshoot. So if we then just dot this across. The value here is going to be 1.015. Okay, and that to there is your AP. Okay. So what else do we need to look at? Let's think in terms of the properties. So the peak time that it takes, the peak time is the time that it takes to get to this peak amplitude is here. So let's put this on. And the peak time worked out was, well, let's actually just label there TP. So TP, or actually you can't see, but I'm putting them down here. Actually, let me move them to over here so you can see, or I'll zoom my camera out slightly. Let me zoom my camera out. So TP is equal to, what do we work TP out to be? 2.6 seconds. Okay. And then TP, you think 1 period, so let's just, this is going to, response could die away. T is 1 period, so T is here. So T was effectively just equal to 5.2 seconds, is just double TP. Okay, so we've got peak time, we've got period time, we've got rise time. So rise time is the first time you hit the final value of the system, so that's given by here. So again, if we just put on TR, so TR we know was equal to 2.08 seconds. Okay, so we've got those three properties. So we've put rise time, we've put peak time, period time, peak overshoot amplitude. Let's put on settling time. So settling time is in 5%. So let's just draw this dotted line. Just add this and then I'll explain. And this here is effectively, because it's plus or minus 5%, that's 0.95. This is 1.05. So the first point in time whereby you get within that, and you can see it's actually like, you can see you've achieved, even in the overshoot, because the overshoot is so short, you actually achieve it here. So settling time TS, and TS is equal to, what's TS equal to? TS is equal to 1.9 seconds. So you can see this is actually all making sense. It's all fitting in nicely. And you can see the number of oscillations to reach TS is here. So it's effectively 0.36, and that kind of makes sense because it's, you're not even obviously anywhere near half cycle. So that's pretty much the sketch there. I hope that this has been a useful example question. So what I have here is a script to check your solution from the previous question. So we'll start off with the usual command, clear CLC, close all. So clear the workspace, clear the command we're doing, close any open figures. So we're going to start off by defining the transfer function. So here's your usual line 7, G is equal to TF transfer function. Numerator here denoted D, and then A, B, and C for the coefficients for the second order transfer function. You'll see here I've defined what A is, so 1, B 3.2, and C is 4, and D is equal to 4 as well. So you can see in terms of the transfer function, that's the form that we saw previously. I'll ignore K for now. But the first, as we did in the hand calculations, the first step is to determine the properties. So in terms of omega, zeta, and omega D. So natural frequency, damping ratio, and the damped frequency. So natural frequency is effectively the square root of C, if you remember. So square root of C, that will give us our natural frequency. Damping ratio is just B divided by 2 multiplied by omega. So again, if you look at the hand calculation, you'll see why that's the case. And then the damped frequency is just the equation that you saw when we did the hand calculation. So if we just run this, let's run that section, clear everything, it's already clear. Run that, you can see our parameters appear here. Then run this, and you can see we work out the natural frequency, omega, the damping ratio, and the damped frequency here, and they are as we worked out in the hand calculations. The next part then is to work out the system performance criteria. So you can see I've literally just written out the equation in terms of for rise time, so 1 over omega d, so you can see there, multiply by pi, take away the invert or a tan inverse tan, multiply by the square root of 1, take away zeta squared over zeta. So you should remember the form of that equation. T is then equal to, you can see, I'm not going to go over every one of these forms, but you can see 2 pi over omega d, and then pi over omega d to give you the peak time. And then you can see the amplitude here, given by this equation, the settling time, and this settling time here is, I'll just make a note, is for 5%, okay, because the value there, 3, that's specific to 5%, and then the number of oscillations for that settling time is given by this equation here. So we can literally click run section, and we can run this, and here you get your values. So rise time, period time, peak amplitude, settling time, and the number of oscillations to achieve that settling time. And you can see the answers match up to what we did, well, the answers that we went through by the hand calculations. So that's all great. This is going to enable you to check your questions or check your answers to the other questions. So for example, in the other 2 questions, you've obviously got different coefficients for D, A, B, and C. So you can obviously change the coefficients here. Make sure you change them here because these here, A, B, C, and D, are used, or some of the coefficients are used in the calculations here. So you need to make sure that you do that. Don't just put them straight in here because you need to define what A, B, C, and D are. And then you can obviously rerun it with the different values and then to get your answer. One thing I should say is if you remember this K value here, value being 1, you can see this is used here because it effectively multiplies by this peak amplitude, because when you haven't got a unit step input, the amplitude of the value is whatever, well, is effectively multiplied by that. Okay, so say for example the final value was 0.1 or the gain value was 0.5 whatever, 0.2 whatever, you put the value there and that would obviously dictate what your final value or your peak amplitude is of the system. So one final thing you can do is you can just click this section, you can run your system response, so you know your hand-drawn sketch at the end. So you could then put a step input into the system, and then what you can do is you can click on the response and you can drag this and you can get amplitude and time values. Okay, so you can see in terms of how this relates to your hand calculations that you've determined and various properties. So I hope this video has been useful. Please contact me if you have any further questions. Thank you.